So routing is forwarding the packet, right? Forwarding the packet from a source to destination. But there's a procedure, there's a logic, there is something involved in moving the packet in a proper direction, in the shortest path, in the best path where the bandwidth is more. It's not just done like that randomly. It has got a procedure. It has got a policy. There is a logic behind routing. That's what I want to explain you today. This will give lot of people who watch this video or who is hearing me now a real deep dive input of how the routing happens, how these MAC addresses and IP addresses are involved in moving a packet. See, there is a plane called control plane. There is another plane called data plane. Control plane, as the word says, control, it controls the path, it controls the packet's direction, it controls the flow of data. It can only control, it cannot move. For moving the packet, we need the data plane to do that. So data can be only controlled by the control plane, cannot be moved by the control plane. Control plane decides the path to be taken and provides the recommendation to the data plane, and it is the data plane the one which is going to decide and push the packet accordingly. So if I need to say in a simple word, there's a program in your watch which is a control plane, and that program on that small motherboard inside your watch makes the small pulleys and the needles to show you time. You may have a digital watch. I'm not talking about a digital watch. Let's say you have a analog kind of watch, like where you have needles, seconds, minutes, and hours. They keep moving and showing you time round the clock. Means 24/7, never stops. It shows the right time always because you have put a battery in it, and the battery makes the program, the control plane, to dictate how this big needle should move, how the small needle should move. Accordingly, those pulleys move and make the needles show you time. The control plane is not making the pulley to spin around. The control plane, the program, only gives command to those hardware component there in what speed they have to rotate. That makes the clock to tick. If you separate the control plane from the data plane, if you separate that program from your watch, the watch won't function. If you separate those hardware components from the motherboard, those pulleys and all, if you remove, then also watch won't function. So there is no use of having control plane separate and data plane separate. They need to work together. They may be in same box, Or the control plane can be somewhere on the top, and there may be many data planes connected to the control plane, and all the devices connected to these data planes are steered, controlled. The data flow is managed. How they need to flow is dictated on what interface it comes and what interface it has to go out. Everything is dictated by this control plane. Now, for routers, what decides the path to be taken is routing table, which is a control plane for routers. Now, routing table will not show you what MAC address to take in order to reach the next hop. Routing table will show in order to go to that destination, this is the exit you need to take, and this will be your next hop gateway address. That's all it will show you. It will show you the exit interface and the next hop. By taking this information, the router has to use the data plane to keep the traffic on that F00 interface, on that exit interface. Like the program in the watch makes that particular pulley to spin around to show you the time. The data has to be placed in that interface on that motherboard, on that particular ASIC chip for the packet to exit. For doing this, you need MAC address because you are dealing with a port, physical port. They're identified with an ID called MAC address, no? So it takes the MAC address and puts as a source of the source of the packet, and the next hop MAC address and puts as a destination. That makes the packet to move from this port to this router's ingress port. Packet was coming from somewhere. This router R1, there are many paths to various destinations. But the destination that you have sent the packet is here behind R1. This router knows that the destination needs to be sent via, let's say, G0 interface. And the gateway address is 10.11.11.2. This is what the two information the routing table is going to provide. The control plane is going to provide. On router 1, when packet arrives, router 1 says you should go out via G00 and you have to meet someone called 10, 11, 11, 29. Sorry, 10,
Hello,
11, 11, 2.
sir.
In routing table, you will have only the exit interface via which the packet should go and the gateway to which means gateway means the next hop, the next device to which the packet should go. And in the adjacency table of the device, you will see the MAC addresses, and also it will copy the MAC address from the ARP table, address resolution protocol. What is ARP? Address resolution protocol. What it does, it uses the IP address and learns the MAC address. For example, You see, we got router 1, router 2, router 3, router 4. And let's say my destination is behind R4, 4.4.4.4. And the source is behind R1, 1.1.1.1. I'll put S and I'll put destination D. If this is 4444, definitely the IP address on this port, let's say this is G1 port, Gig Ethernet 1 port, will be of same subnet 4.4.4. Maybe 3. Now between R4 and R3 there will be a network, let's say 10.34.1, 10.34.0.2/16. See, these ports of the router will also have a MAC address. Let me call the MAC address of this port as AAA and this as BBB. And this computer will also have a MAC address. Let me call this D, 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 C, C, C. We all know MAC address is 48-bit size, hexadecimal. In hexadecimal, it is 12-digit number, the MAC address. I cannot write the 12-digit number. It's waste of time, so I made it a simple AAA, BBB, CCC, and DDD. Assume this is MAC address. And now, between R2 and R3, we got 10.24.0.2 as an IP address. Here 10.24.0.3 is an IP address. So you cannot have different network in same link. You should have same network. Only then they both can talk. So MAC address, for example, here it will be E and F. And say this one as G0 and this one as G1. This one is G0 and this one is G0. These are the interface names. Likewise, 10.12.01/16, 10.12.02/16. This is G0, this is G1, and this is G1. And this port also should have a MAC address and IP address. Let's say 1.1.1.2 on this router's interface. MAC address F, I written so GGG H I. Yep. These are the MAC addresses. Okay, we need one more MAC address for this device, right? Let's write KKK. The IP address of this computer source and MAC address of this computer source. Okay, now you see the source wants to reach destination. So what you did is you went inside the source and said ping 4.4.4.4. That's the destination you want to reach. Now, let us assume these routers are fully converged. What does that mean? These routers know every network in this topology. The routers already learned who is connected where. The routing table of the router is fully updated. Let's assume like that. To update that, we can write static route or dynamic routing protocol, which we'll be seeing a bit later. Today, since it's an introduction to routing, we are learning the fundamentals behind So let us assume the routers know very well every destination and to whom they are connected, what the direction, everything. See, these routers may have many other networks here somewhere. More routers may be connected. I am not drawing all those things because we are learning just fundamental. I am not going to get into uh, big topology. That will be a waste of time. Now, when I ping this, what this computer will do? First thing, it will check whether my address and the destination address in same network. Are they in same network? Someone tell me. Are they in same
Yes,
network? Are you sure?
yes. Yeah, because it's 10 dot.
No, 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 no. Here, the
Okay, but
source is 111. You're pinging from this computer, and the destination is 444. Are they in same network?
no, I don't know.
No. Why? Because this packet, because I'm pinging from this computer, the source is going to be 1.1.1.1. What address I'm pinging? 4444.
Both.
So
Yeah.
definitely not same network. 4 is different, 1 is different. Definitely not same network. Different network. If I have a computer connected like this via a switch 1111 1112 1113. Now let's assume I'm pinging from alpha to gamma. Alpha to gamma source address will be 1.1.1.1, destination address will be 1.1.1.3. Here the network is same,
Yes, sir.
but here it is not same. So when the networks are not same, the computers cannot root root it by itself. The computers don't have that capacity, the knowledge to forward the packet to the destination. The computers depends on the router to which they are connected. That is why we put the IP address of the router as a default gateway in every computer. This is the IP address that will configure on the computer. See, that's the IP address of the router actually. We put it as a gateway address. Why? So that whenever this computer wants to forward the packet to different destination network, it needs to simply send the packet to this address. Who is this address? It's the router. That's the job of a router. What is the job of a router? To take our traffic to different network. Job of a router is to take our traffic from one network to another network. Will computer do that job? No. So we are giving the computers IP address, subnet mask. Along with that, we also give default gateway. And the default gateway will be always the address of the router to which our computer is connected. Fine. Now, if you give the default gateway, it's just an IP address. You are just giving a control plane. This is just a control plane that you are giving, but how it will move the packet to router 1 without knowing router 1's MAC address. This computer will put its own MAC address as a source. KKK, no? Its own MAC address as a source, but the destination MAC address is unknown. But what is the destination it wants to go? It wants to send the packet first to this destination. 1, 1, 1, 2. See, the final destination is this one. the intermediate destination, the immediate destination. In order to reach 4444, first it needs to go from here to the router, because the router is the only one who can take traffic from one network and give it to another network. So what it does is it tries to learn the MAC address of the gateway, for which it will use ARP, address resolution protocol. So it will send an ARP packet. Before sending this packet, it will send an ARP packet asking who is that 1.1.1.2, and ARP reply will come and say it's me, I, which will be there in the MAC table as well as the adjacency table. Adjacent device information will be in adjacency table. Now what this PC will do, it will put the MAC address of R1, which is I, that makes the packet to move from here to here. See the data plane, how it works. Now packet has come to R1. After reaching R1 will receive the packet and see whether this MAC address is matching with its own ingress interface. Yes, it matches. So now what will happen? It will open the layer 3. This is layer 2 information. It will open the layer 3 and it finds that the destination network is 4444 and the routing table's control plane. What is control plane? Router's control plane is routing table. Routing table says to go to 444 you need to take this exit via G0 and your destination should be 10.12.02, means that the intermediate destination. So what router 1 will do now, it will put this G0's MAC address here and the destination, the gateway for R1 is 10.12.02, right? R1 says you need to go to this IP address. But to move the packet, it needs the MAC address. So what R1 does, it again sends the ARP request asking who is the 10.12.02. R2 will say it's me, GGG. So now R1 learns that MAC address of 10.12.02 is GGG. So it is this two addresses, the source and destination, makes the packet move from here to here. Again, router 2 receives the packet, checks whether this MAC address is matching with its own ingress interface. Only if it matches, it opens the packet further and looks into the layer 3 address, which is 4.4.4.4. Check the routing table. Routing table says go out on G0, you will meet 10.24.03. That's what routing table will say. Okay, if I need to go out on G0, what is the MAC address? The data plane says it's FFF. And what is the MAC address of 10.24.03? Data plane says EEE. It has learned via ARP. So now using this to address, the packet moves from here to here. You see, this addresses never change, but this MAC address keeps changing every hop. Now when it goes from R3 to R4, what will be the MAC address? Can someone say?
Source
K.
is CCC, destination is AAA.
Excellent. So it is only the MAC address that moves the packet towards the final destination. The intermediate hops are determined by using the control plane, means using the layer 3 address 4444. But to jump to those intermediate destination, it is the MAC address that is involved. till the packet reaches this final destination. See, now the packet has come to router 4. Router 4 checks whether the MAC address matches with its own ingress. Yes, it matches. And now router 4, what it will do, it will open layer 3 and check the layer 3 address. The layer 3 address is 444 and router 4 says 4? It's my own network. So it sends the ARP request. Is anyone called 4444? And D will say it's me, DDDD, and the packet goes to the final destination. If you are pinging, then what you have sent is an ICMP echo packet, and this will reply with the echo reply. If it is telnet, it will show you the telnet session. Now depends on what protocol that you use to communicate. When I say ping, it is going to use ICMP protocol. It will simply send one echo packet, and if the destination is there, a reply will come. Checking connectivity, ping. So without IP address, you cannot move any packet, because IP address is the one which is going to tell where the packet needs to go. Final destination. And without MAC address also you cannot move the packet, because based on the final destination that you want to go, the path and the next hop is given by the control plane, for which the MAC addresses are used to push the packet to every hop. Here one hop means one router, one routing device. So between every hop the MAC address will keep changing. The layer 2 address will keep changing. The layer 2 encapsulation and decapsulation happens. When R1 sent a packet to R2, it was encapsulating with source MAC address HHH and destination MAC address GGG. Packet got received in R2. R2 decapsulate the packet and see the destination. Destination is GGG. R2 accepts the packet in, checks the routing table. Routing table says you need to send it to router 3, for which the MAC addresses are FFF and EEE. That is what gets encapsulated. And on R3, the packet again get decapsulated, again encapsulated with CCC and AAA. Likewise, for every hop, the layer 2 encapsulation keeps changing. The encapsulation and decapsulation happens every hop, whereas in layer 3, that never happens. Layer 3, till the packet reaches the destination, the source address 1111, destination address 4444 never changes. You see, we need both IP address and the MAC address to route the packet. This is the logic. You need IP address to find the direction via which the packet needs to be forwarded. Now, to move the packet via the direction, you need the MAC addresses, the source and destination, for which it will use the ARP table to know the next hop MAC address and its own exit interface MAC address as a source. That's how the packet moves. Okay, so now let me ask you a question. The packet is going from D to S. Understand the question very well. The packet is going from D to S. If it is going from D to S, what will be the source IP address and destination IP address? Someone tell me, no? What will be the source IP address and destination IP address? The packet is going from D to S. Why, Sila? Is it that difficult question I asked?
Source is D
I know what is the IP address of source.
by IP address.
Here I have written right 4444.
444.4.4.4.
Destination.
Uh, Destination 4.4.3.
No, 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 no. I'm going
One
from
destination
yeah,
1.1.1.
yeah, 1.1.1.1. I'm going from D to S. So S is 1.1.1.1. Fine. Now this is the layer 3 information. What will be the, understand the question, what will be the source and destination MAC address if the packet is currently in R3? What will be the source and destination MAC address if the packet is currently in router 3? See, by using a lot of MAC address, packet has jumped from here to here, here to here. Now it has come here. It's in R3 now. If the packet needs to go to 1111, what will be the layer 2 information? When R3 sends the packet, what will be the layer 2 information? What will be the source and destination MAC address?
Is it EE?
Exactly. E. And destination MAC address will be
It's it's K or what you have given?
this one.
No, destination will be F.
Very correct. F. Right? So MAC address will not be KKK. It cannot jump like that. First, it has to jump to the next hop. So it will be FFF. Okay. So this question I asked you so that I'll know whether you understood it, but not that much clear. Everyone were silent for a long time. So let me put the question in another way. Similar question. You see, there is a packet. Sorry, there is another network here. Um, the computer's IP address is here. It is 220.1.1.2. The IP address of the computer is 20.1.1.1. The MAC address is alpha. The MAC address here is beta. And the port name is E0. Okay, now this is M computer and this one is D computer. So M wants to talk to D. M wants to talk to D. The question is, what will be the source IP address and destination IP address, source MAC address and destination MAC address when packet is currently in R3? Packet is right now in R3. M is talking to D. What will be the source, destination, IP address, and MAC address? No, cannot take this long time. Abhi, can you tell? Okay, anyone can try. If you are in mute, unmute and talk. I cannot hear you.
Source is 10.34.0.1.
Source is 10.34. See, we are going from M
So
to
20
T. What will be the source
see
IP address and destination IP address? Right now, our
source
packet
is
is in router 3.
M.
Okay, tell me, what is the source?
It's 20.
Very good. See, the IP address will
Yeah.
never change, I said. The
Wait,
source is 20. Okay, destination?
destination is the address you have given, like 10,
No, no,
20.11.
no, no, no. D. D's address is what? I'm talking about the layer 3 address. You're going from M to
4.
T. 4.4.4.4.
Okay, 4.4.4.
What's the source MAC address? When I right now,
Source
the packet is not here now. It has already moved from here to here, here to here. Currently, the packet is in R3. What will be the source MAC address and destination MAC
R3
address?
CCC
Very nice.
CCC.
What is the destination MAC address?
Destination will be R, then R4, no?
Tell me the MAC address, please.
A A
Exactly.
A.
AAE. You see, this computer, IP address, let's say 10.0.0.1, connected to a router whose address is 10.0.0.2. And this router is connected to, let's say, another computer here, 20.0.0.1, 20.0.0.2. And this interface IP, the MAC address, let's say AAA, this is BBB. And let's say the gateway, not let's say, gateway will be always the router's address, 10.0.0.2. This computer also has got a MAC address. Let us call it as gamma, gamma, gamma. And this computer also has got a MAC address. Let's call it as theta, theta, theta. Right. Now, alpha wants to talk to theta, which means what? The layer 3 source address is 10.0.0.1. Layer 3 destination IP address is 20.0.0.1. And now the source MAC address it knows because it is its own MAC address. It knows alpha, gamma, gamma, gamma. But the destination MAC address is unknown. It wants to send the packet to 10.0.0.2. It knows, operating system knows that if the networks are not same, see this is 10 network, this is 20 network. Operating system knows, any operating system, it can be Windows or Linux or whoever, whatever. The operating system knows that I need to take the help of the gateway, the router's address. So it wants to send to router, but it don't know the MAC address of the router. So what it will do, it will send a layer 2 broadcast. That is what ARP does. ARP, address resolution protocol. It will send a layer 2 broadcast. Broadcast means what? Sending to anyone. Whoever receives the packet should respond. So this computer, what it does, it sends the broadcast. Hey, who is that 10.0.0.2? Kindly reply. And it goes as a broadcast because it is sent as a broadcast. Even if you have many computers here, they all will receive it, including this port on the router, because it's a broadcast. The switches will flood it. Even if you don't have switch, it will be easily received by the router. So the router receives the broadcast, and the broadcast says, "Who is the 10002?" The router says, "It's me. I have to respond back now." So it replies. We call it as ARP reply. The ARP request was sent as a layer 2 broadcast, and ARP reply comes as a unicast. It it responds to gamma gamma gamma, saying I'm AAA. Router says I'm AAA to gamma gamma gamma. It's only a layer 2 communication. That's how the ARP in this computer, if you check the ARP table, ARP-A, this is the command. Say for example, let me put it in my computer and show you command prompt. ARP-A. You see? I have the MAC addresses of my router. You see? I should not show these things in YouTube videos because there are good people as well as bad people who can use the MAC address to damage my network. Anyway, this is how the MAC address of 10002 is learned using ARP. ARP request is sent as a broadcast. Everyone receives it. Only 10002 will respond because the ARP says, "Who is 10002?" So the router says, "It's me. My MAC address is AAA." And now AAA is assigned as a destination MAC address. Packet can jump from here to here. After packet coming here, the router says, if you want to go to 20, you need to exit on this end of this via this port, and you need to go to this address. So it uses the MAC address BBB, and same ARP will resolve the MAC address of 20001. That is how it knows theta, and the packet goes out. You see, the IP address will show only the direction. To move the traffic via the direction, you need MAC address. Both addresses are important for the packet to be forwarded. And we all know size of MAC address is 48-bit and size of IP address is 32-bit. Can someone say the size of IPv6 address? No need to give chance for others. You can tell me, please, because we cannot wait long. What's the size of IPv6 address? Unmute. Maybe you're in mute, you're telling answer. What is the size of IPv6 address? 128. MAC address? What is the size of MAC address?
You said no, no, that
No.
10.
What is the size of MAC address? Others. Don't forget these numbers, though it is a silly question, but it is again an important question. Because when we know big stuff and when we don't know the small thing, people will underestimate us. MAC address is 48-bit size, IP address is 32-bit size. All right, so we'll stop here today. We'll continue this. We are going to get into routing tomorrow. Today, I just introduced you the importance of MAC address and IP address in routing. But
Okay, sir.
how the router knows the route? There are two ways. One, we give statically the routes. Number two, we enable dynamic routing protocols like RIP, Routing Information Protocol, EIGRP, Enhanced Interior Gateway Routing Protocol, OSPF, Open Shortest Path First, And we also have BGP and ISIS, which will learn the routes dynamically and install the routes into the routing table. This is what we are going to see in coming days. Thanks for joining. If you don't have any question, we'll close here. Any question from anyone?
So this question is like you were saying like ARP.
Hmm.
So all these computers are doing the same thing, no?
Yeah,
Requesting and all.
every hop, but not all the
Traffic.
time. Only once it will do, and learn the MAC address and save the MAC address in the ARP table. And
Okay, once it is saved, like it will only refer, right?
yeah, it will only
It
refer.
will not.
Correct.
So that will not create that much traffic. Hope so.
Not at all. Only one time. First time.
One time.
Yeah.
Okay.
All right. Any other question? Fine. See you tomorrow. Same time. Take care.
Okay,
Bye.
sir. You will send this, no?
Yeah, we
All the